Have you ever wondered what happens when two waves travels in the same medium? Will the two waves bounce off to each other, or they pass through to each other? Or will the meeting of waves affect the appearance of the medium? So these questions about the meeting of waves pertain to the topic of wave interference. Here's our learning outcomes for today's discussion. At the end of this lesson, learners will be able to define wave interference and its types, explain interference through experiments and real-life examples, solve problems, and identify applications of wave interference. So without further ado, let's start. What is wave interference? It is a phenomenon in which two or more waves superpose to form a resultant wave of greater, lower, or the same amplitude. Meaning to say, it is between two or more waves, which is they overlap to form something, whether this wave is a greater wave, dako, lower wave, or this wave has the same amplitude. Or meaning, equal lang siya. In the left image, it is before interference. So these waves are separated, one with the blue and one with the red. They are moving toward each other. Each wave has its own amplitude, has its own shape, and they are not yet overlapping. While in the right image, it is during interference, the two waves overlap at the same point in space. Their displacements add together, and this is according to the principle of superposition. The green wave shows the resultant wave, which is larger because the crest of one wave has combined with the crest of the other. And mamit ni nato siya unya sa types of interference. And kani siya ang akong gipakita example is an example of constructive interference. Next, what is the principle of superposition of waves? The principle of superposition of waves is when two or more waves of the same type are incident on the same point. The resultant amplitude of that point is equal to the vector sum of the amplitudes of the individual waves. Meaning to say, waves meet at the same point in the medium. They do not cancel or destroy one another. Instead, they combine their effects, and the displacement of the medium at that point is simply the sum of the displacement from each wave. After the wave passed through the medium, it returns to its original state as if nothing happened. There are some conditions for interference to occur. First is coherent sources. Waves must come from sources that maintain a constant phase difference with the same frequency. Without coherence, the interference pattern will not be stable. Next is the same. It must be having the same type of waves. The waves must be of the same type. Example, it should be light waves, both should be sound waves. Next is same frequency or nearly the same. For sustained interference, the wave must have the same frequency. If the frequency is slightly different, you get peaks instead of stable interference pattern. Next is comparable amplitude. So, meaning to say that amplitudes of waves should be nearly equal for a clear pattern of bright and dark or loud and soft regions. Lastly, it must having a proper path difference. So, waves should meet at a point where the path difference allows constructive or destructive interference to be observed.
So now we are on the types of wave interference, and there are two, constructive and destructive. So let's begin with constructive. So constructive interference happens when waves are in phase with each other. Our keyword there is in phase. So meaning their peaks or their crests and troughs align. So in this case, the resultant wave will have an amplitude that is sum of the individual wave amplitudes, meaning mag-add up sila. And we have destructive interference, which occurs when waves are out of phase. Kung kaganina in phase, now they are out of phase when the peak or the crest of one wave coincides with the trough of another. So when this happens, the waves cancel each other out, resulting in reduced amplitude or in some cases, complete cancellation. I have here a diagram to understand better. So you can see there, if positive 1 in the crest, the letter A overlaps with the B, positive 1A gap on the amplitude, so meaning they are in phase, so they will create a bigger wave. So for example is a concert speaker. So when two speakers play the same note in sync, the sound waves add up, so meaning mas mapusog siya. At some spots in the audience, the sound is much louder because of constructive interference. So destructive interference dayon is the opposite. If you try to look at letter A, na siya cross niya negative 1A, nag-meet dayon siya sa letter B na positive 1A, which is the crests. So if they overlap, what will happen? Ma-flatline na yun siya. Tama? So we have example dayon is noise cancellation sa tong headphones na mechanism. So they produce a mirror sound wave that cancels incoming noise. So the result dayon ana, the unwanted sound is reduced or eliminated. So mas clearer din ang atong matungog. And quiet spots in a concert hall, for example. So at certain positions, sound waves from speakers cancel out. You might notice areas where the music sounds weaker or almost silent. So let's summarize the two types of wave interference. The constructive interference, they look exactly the same, same size, same timing, and so when they overlap, they add together. So crest to crest, so bigger ang iyang crest. Trough to trough, deeper ang iyang trough. So instead of a height, for example A or 1A, the wave now has 2 A with two amplitudes. So this is called constructive interference. So the wave gets stronger. And the destructive dione, the shift means one wave's crest is always at the other's trough. Let's just remember that when we have two waves and the other one is shifted by 180 degree or a half wavelength, it is destructive. So when they overlap, they cancel each other out. So crests to trough, flat line. So trough to crest, flat line as well. So the result is no wave at all, and young amplitude is equal to 0. So that's what we call the destructive interference. The wave gets weaker or it disappears.
Hi everyone, I will be discussing the Young double-slit experiment. So, during the year 1801, Thomas Young carried out an experiment where the wave and particle of nature of light and matter were demonstrated. So to find out, he designed the famous double-slit experiment. So by letting light pass through two narrow slits, he observed the bright and dark interference stripes on the screen. Thomas Young wanted to test whether light was made of particles, as Newton believed, or if it behaved like waves. So he set up a light source and allowed the light to pass through a single narrow slit first. This was to make sure that light waves were coming out neat and in step with each other. He then placed a second barrier with two tiny slits side by side. Finally, behind that barrier, he placed a white screen to capture the result. So when the light passed through the two slits, each slit acted like a new source of light waves. So you can imagine it like throwing two stones into a pond and watching the ripples spread out from both points. So as these two sets of light waves spread out and met each other on the screen, two results came out. One is where the crest and throws match, so they combine to form bright spots. Two is where a crest met a throw, so they cancel each other, leaving dark spots. So instead of just seeing two bright patches of light, which would have been expected if light were only particles, Young observed a series of bright and dark stripes. So this pattern is called an interference pattern, and it was clear evidence that light behaves like a wave. So the experiment is highly significant because it provided direct evidence of the wave nature of light. So before this, many scientists thought of light only as particles. So Young experiments show that light can interfere just like water waves or sound waves, proving it must have wave-like properties. So mathematically, the spacing between the bright fringes is given by the formula, where lambda is the wavelength of light, L is the distance from the slits to the screen, and D is the distance between the slits. So this experiment perfectly demonstrates the principle of wave interference, which is the overlapping of two or more waves in space, resulting in regions of reinforcement or black fringes and cancellation or dark fringes. So it connects directly to the idea that light, sound, and even water waves all follow the same interference principle.
Good day everyone. Today I'll be discussing thin film interference. So when light hits a thin transparent film like a soap bubble, an oil slick, or even a coating on glass, something interesting happens. Part of the light reflects off the top surface of the film, while the rest of it goes inside, reflects off the bottom surface, and then comes back out. Now we have two reflected light waves, one from the top surface and one from the bottom surface. So these two waves overlap, and depending on how they meet, so they can either add up or cancel out. This is what we call interference. So why do they interfere differently? So the interference depends on two main factors. Number one is path difference. The wave that goes into the film travels a slightly longer path before coming out. If this extra distance is a whole number multiple of the wavelength, the waves line up is constructive interference or bright colors. So if it's a half wavelength or an odd multiple, they cancel. So it is destructive interference or dark or absent colors. So number two is phase shift during reflection. When light reflects off a denser medium, it flips, like adding a 180 degrees phase shift. So this extra shift can change what would have been constructive interference into destructive and vice versa. So the result is colorful patterns. So since different wavelengths or colors of light are affected differently by thickness, the film produces brilliant rainbow-like patterns. That's why we see swirls of color in soap, bubbles, and oil films. So, real-life examples are soap bubbles. As the bubble stretches, the thickness changes and the colors shift. Oil spills on water. The thin oil layer creates rainbow patterns under sunlight. And anti-reflective coatings on eyeglasses. Engineers design the coating so reflections cancel out, reducing glare. So to pack it all, thin film interference happens because light waves reflecting from the top and bottom surfaces of a thin layer overlap depending on the thickness and wavelength. The waves can either reinforce each other, producing bright colors, or cancel each other, leaving dark spots. So that's all. Thank you.
Now let's move on to the application and problem solving. Now let's have first. Two waves traveling in the same medium have amplitudes of 3 cm and 4 cm. If they interfere constructively, what is the amplitude of the resulting wave? Now, let's use the formula for the constructive interference, which is A total is equal to A1 plus A2. Because when two waves interfere constructively, their amplitudes add. So the given are 3 cm and 4 cm. So you just need to add those values. So you're going to, step 2 is you're going to plug in the values. So A total is equal to 3 cm plus 4 cm and equals to 7 cm. So that's easy, right? Okay, now let's move on to the second problem. Now, two slits are separated by a distance of 0.5 mm and the screen is placed 2.0 meter away. If the wavelength of light used is 600 nanometer, what is the position of the third bright fringe? So let's first have the given. The distance between slits is 0.5 mm and convert that into meters, 0.0005 meters or 0.5 times 10 to the negative power of 3, and the distance of screen is 2.0 meters. And the wavelength of light is 600 nanometer, and again convert that into meters, you'll have 600 times 10 to the negative power of 9 meters. And you're going to use the third bright fringe. So the formula of Young's double slit experiment now tells us how far each bright spot or fringe appears on the screen. So the third fringe is just 3 times farther than the first one. So we multiply the wavelength, the screen distance, the fringe number, then divide by how far apart the slits are. So or the length. That gives us the position on of the fringe now. So now that we get the values or the given, let's plug into these values to the formula. So you'll get there 3 times 600 times 10 to the negative power of 9 times 2.0 divided by 0.0005 or 0.5 times 10 to the negative power of 3. So if we're going to calculate that, you're going to get 3.6 times 10 to the negative power of 6 divided by 0.5 times 10 to the negative power of 3. And calculate that again, you'll get 0.00072 meters. And then convert that into millimeters, you'll get 7.2 millimeters. That's all.